This video is a continuation of episode 4. We talked about the concept of tasks, utility theory, and how we can organize these tasks into behavior trees. This was a fine video to get the basics. However, the task system that we created is not really ready for production. It has a lot of room for errors, and most of all, it's really hard to visualize what it's doing. In this video, we're going to fix all of these problems. We're going to make our behavior tree system more reliable, ready for production, and ready to take a beating. Because if you want to create more advanced behaviors, if you're really serious about creating interesting game AI and NPCs for your games, then you absolutely have to make sure that your behavior tree system is rock solid, that you can rely on it to deliver the value that you want and allow you to create the content that you want for your game. By the way, thanks for subscribing. We've reached 204 subs today and the channel is still growing. Before we continue, it's important to understand how game AI works in any game. So game AI works in layers. First, we have the foundation layer, which is made of systems such as locomotion. So how your characters move, how they are animated, how they turn. Then we can have pathfinding. For now, we're using Unity's AI pathfinding system. But instead of that, we could be using something else. We have things such as sight, hearing, and other foundational systems. Then on top of the foundation, we have our systems. So this is how we organize the code to use the layer below. We could use FSMs, behavior trees, and in these behavior trees, we could implement custom tasks. Then on top of these layers, we have the actual content of your game. This is where we define the actual behaviors of your NPCs. For example, your guards, your zombies, your shoppers, your civilians, your colonists, anything that pertains to your game. And the content layer will use the systems below to create the actual game AI of your game. I should say a word about Behavior Designer. This is a paid asset on the asset store. There's also Playmaker and Node Canvas. All these tools allow you to create behavior trees and finite state machines in a visual way. They're well tested, and actually I've been using Behavior Designer for years along with Playmaker. They're amazing to organize your code, to quickly get something visual. However, there's also a lot of value in creating these systems from scratch. And in fact, what we're going to be doing is adding some features that don't even exist in these tools. So there is a lot to learn by making your own systems. However, I'm not against using Behavior Designer. In fact, you'll find that making custom tasks for our system and for Behavior Designer is very similar because I use almost the same syntax that Behavior Designer uses. A behavior tree is a hierarchy of tasks that start at the root. A task can be either an action, condition, decorator, or composite. So far in our code, we don't distinguish between actions and conditions, so we simply inherit from task, but now we're going to define action and condition. The actions and conditions are actually the leaf tasks. They don't have any children. Composite tasks can have one or many children. As for the decorators, they can have one child and one child only. In the previous video, we defined two actions, wait and log. We're actually going to make them inherit from the action class this time, not the task class. As for the conditions, they're similar to actions. However, they only return success or failure. You can think of them as if statements. And for the decorators, we created the repeater decorator. And for the composite tasks, we created sequence and UtilitySelector. Most of our gameplay code will be organized in custom actions and conditions. And more specifically, we'll create actions that inherit from NPC action and conditions that inherit from NPC condition. In this video, we'll create some new tasks. Now let me explain how all of these tasks work with a quick recap on the tasks we created before. A sequence will run its child tasks one after the other, so it will execute A. When this succeeds, it will move on to B. When this one succeeds, it will move on to C. If at any point one of the tasks fails, then the whole sequence will fail. If B returns a failure, which means B has failed, then the whole sequence will stop and return a failure. Now let's talk about the selector. It will execute the tasks one after the other. So as long as the children return failure, the selector will keep going until one of the children returns a success. Now let's talk about parallel. The parallel task will run all of its children simultaneously and will fail if one of its children fails. So in that regard, it's similar to a sequence. Then we have have a parallel selector. Much like the parallel task, it will execute all of its children at the same time. However, when one of its child tasks succeeds, then the parallel will stop and return a success status. In that regard, it's similar to a selector. Then we have our utility selector. So utility is like a score, like we discussed previously. The utility selector will call getUtility on each of its child tasks. Then it will pick the child task with the highest utility, and that's the task that will be running. If at any point another child task has a higher utility, the utility selector will interrupt the current task and will switch to the task with the highest utility. Now let's talk about our decorators. In our previous video, we implemented a repeater such as it repeats the child task indefinitely. Now we're going to add the option of either repeat forever or repeat a set number of times. Now let's talk about the RandomChance decorator. Unreal Engine has a decorator with the same name, so I was inspired by that. This decorator has a random chance, for example 50%. Depending on this chance, it will choose to execute the child task or not. And here we have the idle action. So what this action does is very simple. It will simply return the running state always, all the time. And this will be helpful in a lot of scenarios, as we will discover later. So what are we looking at here? What is the end result that we want to achieve? In the scene, I have two characters. Each character has a different behavior tree. Let's go into the AI controller for each character. Here I have an AI controller script, an NPC sensor, and a behavior tree component. This is a new component that we're going to see in more detail. The behavior tree has a reference to an external behavior tree. These behavior trees are scriptable objects. I've organized them in this folder. If you go to Content, Behavior Trees, here we have Guard and Turning Test. These scriptable objects can have parameters. For example, Guard has Wonder parameters that we defined in earlier videos. So by changing the external behavior tree that an NPC uses, we are effectively changing the whole behavior of that NPC. From the behavior tree inspector, we have a button to open a viewer. We can only see the behavior tree when we're running the game. The tasks in the behavior tree could be using some values, for example, some float or some boolean or some game object. And if we want the behavior tree to expose these values in the inspector, they will be shown here. So I'm going to run the game. As you can see here, this is the behavior tree of this character. This is the guard behavior tree. And in data, we have main target, which is none at the moment. I'm not going to dive deep into this behavior tree because we're going to see it in detail later. Right now, our focus is the improved task system. So I've organized all the scripts in the task system in this task system folder. We have a base subfolder with the task base class and the 4 tasks that inherit from it. We have a behavior tree folder where we have the behavior tree component, the behavior tree viewer, and the external behavior tree, which is a scriptable object. Then I've created a behavior tree editor in order to create this custom inspector. In the data subfolder, we have shared variable, behavior tree data, and shared variable list. These classes are used by the tasks to communicate with each other. For example, if we want a task to choose a destination and another task to go to that destination, rather than a simple vector tree, we'll use a shared vector tree, and we'll see how this works. Then we have our tasks, we have our actions, idle, log, wait, our composites, parallel, sequence, and utility selector. I will talk about the other types of composites in another video. Right now, these are the composites that I'm actually using in the guard AI behavior. Then we have our decorators, RandomChance, and repeater. So these are the scripts that we're going to look at today. Let's improve the task class. In the task status enum, we're going to add another value called inactive, which will indicate if a task has not been started yet or if it has been stopped after executing. Because in fact now we not only return this status in the onUpdate method, but we also store it within the task. So a task will have a status variable set to taskStatus.inactive by default. I'm also defining an active property that will return true if the status is not inactive. Then we add another method to compare the status. Okay, let's fold this region. We're going to add a reference to the owner of the behavior tree to which this task belongs. So we add an owner property of type GameObject. We'll make it protected. Then we'll add a setOwner method and we set it to virtual to allow child tasks, for example, composites and decorators, to override this method and call setOwner on their children as well. Why we need a reference to the owner of the behavior tree? That's because now in the virtual methods of the task, we have an onAwake method. The purpose of the onAwake is to act like a constructor. After the owner is set and after everything has been initialized, the behavior tree will call onAwake on each of its tasks. When we make custom actions, we will not necessarily have access to the game object on which the behavior tree is. So in the onAwake method, we'll have an opportunity to get any component we want from the NPC's hierarchy. You may ask the question, why don't we have access to the game object on which this task is defined? Like we did before we created a guard AI controller script and we created all the tasks within it and our guard behavior tree. So we could just have access to it. We could get a component and assign it to the task. But now we want to evolve our task system. We want the possibility of having external behavior trees that are in the form of scriptable objects. So in the constructor of our tasks, we may not have access to a game object then. However, we will have access to that object in the onAwake method. And in the getUtility method, instead of returning 0 by default, we return a default utility, which is a public float. Here I wrote a comment. You can set the default utility of any task without having to override it by setting this value. For example, previously, if you wanted to set the utility of a sequence, you'll have to have a custom child task where you define the utility. With this value, that won't be necessary. Each task that overrides getUtility has the freedom to choose what to do with this value. They can add it to another value, return their own, or do anything they want with it. Previously, you had to override the getUtility method to set the utility of this task or the composite or decorator that owns that task. Now you can just set the default utility value. For example, if you have a wander behavior and some NPCs need to give it a utility of 5, while others need to give it a utility of 2, then you can do it with this value without having to create 2 separate classes for each wander behavior. Maybe you've noticed that in here, almost all of these methods are protected. So I ran into a lot of issues by having onEntry, onExit, and onUpdate as public methods, because you're not supposed to call them from external scripts, especially when our custom actions do stuff in the onEntry, onExit, and onUpdate methods. So they change the state of the game, they change the state of the NPC, and they implement some gameplay code. It's very easy to make the mistake of calling onUpdate, for example, when you shouldn't. So for example, if a task is inactive, you shouldn't be calling onUpdate. And I did spend hours debugging some really tough problems before coming up with this solution. So the first part of my solution was to absolutely make these methods protected. Nothing outside of task should have access to them. However, for the onDrawGizmos methods and the getUtility method, it's okay to have it as a public method. Before moving on, I'm also going to define a hasAwakened boolean. We're going to use this boolean as a flag. So when a task has awakened, when we've called the onAwake method of that task, we will set this boolean to true. And if we try to call onAwake again, we'll print an error message on the console. So instead of doing it the error-prone way of having these methods as public and giving ourselves the opportunity to make mistakes, instead I've defined some static methods that will do this for us. Here are the static methods. We have awaken, start, stop, restart, and update. What these methods will do is they will call the virtual methods of the task like onUpdate, onEntry, onExit, but they'll do it only when appropriate. And if it's not appropriate to do so, we will print errors on the console. Let's start with the awaken method. First, we check if the task is null. We print an error message and we return. Then we check if the task has already been awakened. I'll talk about the full name property that I'm using here shortly. Then at the end, we'll call onAwake and we'll set the hasAwakened boolean to true. Then we have the start method. First, again, we check if the task is null and print an error message. Then we check if the task has not been awakened. We should not be calling any of these methods if the task has not been awakened. So we print an error message. Then we check if the task is in the running status. Then it should not be started. So we print an error message. Then at the end, we set the status of the task to the running status and we call its onEntry method. We do the same thing for the stop method. So again, we check if the task is not null. We check if it hasn't been awakened and we print an error message. Then we compare the status with the inactive status. If it's inactive, it means means either that it hasn't been started yet or it has already been stopped, so we cannot call stop on it. Then finally, we set the status to the inactive status and we call its onExit method. In the restart method, we check if the task is in the inactive status, then we call it start method, otherwise we call stop and then we call start. In the update method, again, we're going to check if the task is null. If so, we're going to return the failure status. If the status of the task is success or failure, we do nothing. We simply return the status of the task. That's because it's the responsibility of the parent task to handle this status and stop the task. Then if the status is inactive, we print an error message. We should not be updating an inactive task. And we return the inactive status. Then we call the onUpdate method of the task. We save its status in a status variable, then set the status of the task to that status variable, and then we return the status. So with the help of all of these checks and error messages, we will make sure that our behavior tree is rock solid. So we should not, under any circumstance, be getting an error message on the console. But if we do, we will use that to investigate the problem and fix the behavior tree. That's actually how I did it. I spent a lot of hours implementing tasks and behavior trees. And as soon as I got an error message, I would go back and investigate why that problem occurred. However, most of these error messages will only happen on our composites and decorators, and since we're going to be only making them once and most of our gameplay code will be in custom actions and conditions, once you fix all the problems with your composites and decorators, then you can be 100% sure that your behavior tree will behave exactly as you want without any errors. Now let's define a few properties that we're going to use for debugging. We'll also use them in our behavior tree viewer. We start by defining a name, which is a virtual property that the child classes can override. This is useful if you want to give your task a specific name. For example, if you have a sequence of your NPC going to grab a bagel, then you would call that sequence grab bagel sequence or something like that. So here you would set grab bagel as a name, and what's actually displayed by the viewer is the full name. If name is empty, we'll display the class name of the task, and if name is not empty, we'll return a string with the name and then the class name between parentheses. And finally, we define an eternal boolean that indicates whether the task should be folded in or out in the viewer. We'll talk more about this when we get to implementing the viewer. Now let's talk about the four main tasks that inherit from the task class. Here we have action, which we can keep empty. Same thing for the condition. When we derive from these classes, the value is that we can use reflection in C# to know exactly what a child class is. We will know if this class is a condition or if it's an action. And we'll use conditions later for what's called interruptions, where we can interrupt some branches in the behavior tree, but we'll dive deeper into this in later episodes. Now let's explore changes in the decorator task. We override the setOwner method. So we set the owner of the decorator, then set the owner of the child as well. Then we define the onAwake method, which calls task.awaken on the child. Then we have the onEntry method, which calls task.start on the child, and the onExit method, which checks if the child is active, then calls task.stop on the child. And now let's see the changes on the composite task. We override the setOwner method. We set the owner of the composite itself. Then for each child task, we call setOwner on it. We override the onAwake method, where we loop through the child tasks and call task.awaken on them. We override the onExit method, where for each child task, if the child task is active, we call task.stop on it. Then we override the getUtility method. However, now when we return the value, we return the max utility that we found plus the default utility of the task. Now let's look at our tasks. In the actions, we have the idle action. It will simply return the running state always. We have our log action. Log and wait haven't changed since the last episode. This is parallel, which inherits from composite. In its onUpdate method, we first check if the task count is 0 and we return failure. Then for each task, if the task is not active, we continue. Then we call the update method. If the return status is a failure, we stop the task and return failure. And if the status is a success, we stop the task. Then when we're out of the loop, we return the running status. And here in the onEntry method, for each task, we're going to start it. Then we override the onDrawGizmos and onDrawGizmosSelected. We're going to loop through the list of tasks. If a task is active, we're going to call the method of the same name on that task. This is our sequence, which inherits from Composite. We define a current task index variable, then a current task property, which returns the task at current task index. We catch any errors that may occur here, and we print an error message on the console. Then we define a method isCurrentTaskIndexValid, which checks if the current task index is between 0 and taskCounts -1. Then we override the onDrawGizmos methods. We check if the current task is valid. Then we call onDrawGizmos on the current task, same for onDrawGizmosSelected. We override the onEntry method where we set the current task index to 0. So when the sequence starts, we want the current task index to be 0. Then if the current task index is valid, we start the task using task.start. We don't have to override the onExit method because the base composite task will automatically stop any running child. Then we override the onUpdate method. Here we check if the task count is 0 and we return failure. Then we call the update method and we return the status. If status is a success, we stop the current task and we increase the current task index by 1. If we've reached the end of the sequence, current task index will be equal to tasks.count and we return a success. Otherwise, we start the current task, and if the status is a failure, we stop the current task and we return a failure. And by default, we return the running status. And this is our utility selector, which also inherits from Composite. I moved the select task by utility from the task base class to this class. As for the rest of the code, we have the current task here. In the onEntry method, we set the current task to null. Here again, no need to override the onExit method because the base composite task takes care of that. Here we have the onDrawGizmos and onDrawGizmosSelected. If the current task is not null, we call the method by the same name on it. And for the getUtility method, we simply return the utility of the current task. Otherwise, we return the default utility. In the onUpdate method, we call selectTask. If the current task is not null, we update it. If the return status is a success, we stop the current task and return a success. Because remember, the utility selector is a selector. If the current task succeeds, then the whole selector succeeds. Otherwise, if the status is a failure, we stop the current task, then set the current task to null, and we return the running status by default. So here when we set the current task to null, in the selectTask method here, we'll have a chance to update the current task variable. So here we pick the best task by using selectTask by utility. If the best task is null, we print an error message. If the base task is the same as our current task, we simply return. We don't need to do anything. However, if the current task is not null and the current task is active, we stop it. So here we could simplify this syntax. We could simply say if current task is active, since we've defined the active property. At this point, we assign best task to our current task variable and we start it. This is the RandomChance decorator. We define a chance variable, which is a float. Then we define a boolean where we're going to store whether the chance is successful or not. We define a constructor that takes the child task as the first parameter and the chance as a second parameter. We define a method called evaluateChance that we're going to use to check whether the chance is successful or not. If chance is lower or equal to 0, we're going to return false. If it's greater or equal to 1, we'll return true. Otherwise, we'll only return true if chance is superior to random.range between 0 and 1. In the onEntry method, we'll call evaluateChance. If it returns true, we're going to set chance is successful to true, and we're going to start the child. Otherwise, we set our chance is success variable to false. In the update method, if child is null, we're going to return a failure. This should never happen. If our chance is success variable is equal to false, we're going to return the success status. Otherwise, we're going to update a child. If the return status is a success or failure, we're going to stop the child and return that status. Otherwise, we return the running status. Let's improve the repeater decorator. Let's define a repeat forever boolean. Then, if that boolean is set to false, we're going to need a number of iterations that the repeater should repeat and a random value if we want this number of iterations to be randomized. And we define a boolean end on failure. If this value is true, if the child task ends on a failure, the repeater will also end on a failure. We need a private variable to track the number of times that the repeater has iterated. This is the new constructor. In the onEntry method, we call the base onEntry method of the decorator. Then we set times to repeat to iteration plus random range between 0 and iteration random plus 1. Now let's look at the onUpdate method. First, of course, if the child is null, we return a task status of failure. Then we call update on the child and we store the status in a status variable. If the child has returned a failure status and end on failure is set to true, we're going to stop the child and return a failure status. Here we define a child finished boolean, which will be true when the status is either a success or failure. If repeat forever and child finished are both true, we're going to restart the child. If we're not repeating forever and the child has finished, we're going to decrement times to repeat and stop the child. If times to repeat has reached 0, we're going to return a task status of success. Otherwise, we're going to start the child again. That's it for this video. In the next one, we're going to talk about the behavior tree component, the viewer, the concept of blackboards and shared variables, and we're going to finish implementing our production-ready behavior tree. Until then, see you later.